Hello everyone. In this problem, we are given a grid of zeros and ones. A 0 represents an open space, and a 1 represents an obstacle. Starting in the top right corner and only moving down or right, return the number of unique ways you can reach the bottom right corner without encountering an obstacle. So for this example here, we would return 1, because there is only one path you can take to the bottom right corner, which I've highlighted in green. In this example, we would return 0 because there are no ways to reach the bottom right corner. And in this example, there are 3 different paths to get to the bottom right. Some constraints are the top left corner and bottom right corner will contain no obstacles, and you are not allowed to modify the input grid given to you. Now that you understand the problem, let's try and come up with a solution. We can break this problem into subproblems. The answer to how many ways to form the bottom right is equal to the number of ways to get to the cell above it, plus the number of ways to get to the cell to the left of it. More generally, for any cell ij, the answer is the number of paths from the cell above plus the cell to the left. The fact that we can solve the answer to the unique paths question to a cell with the same unique paths question to different cells points towards a recursive solution. Here's the solution. In the original call to the helper function, we tried to solve the subproblem for the bottom right corner. In our helper function, this is where we will do the recursion. The base cases are if we are out of bounds, or if we have run into an obstacle, then we return 0 because there are no paths that come from an out of bounds position or a position with an obstacle in it. The other base case is if we are in the top left corner, there is one way to reach the top left corner, just starting there, so we return 1. And then we have the recursive case. For all other positions, we make a recursive call for the cell above and the cell to the left. For the time complexity of the solution, it is exponential, with the base being the amount of branches spawned with each recursive call, and the exponent being the max depth of recursion. In this case, the amount of branches is 2, and the max depth is the width plus the height of the grid. For space, we have the extra space used by the recursive stack, which worst case gets to the max depth, which is n plus m. As with most recursive solutions, we can easily improve the solution by introducing memoization. Here's what the code would look like. The changes are that we initialize and pass in a memo of the same dimensions as the grid. All the values of the memo start with -1 to symbolize that they have not been computed yet. And then in our helper function, we add an extra check to see if the value has already been computed. If it has, then we can just exit early and return the already computed value. If the value hasn't been computed yet, then we need to compute it and store it in our memo before returning. This knocks down our time complexity from exponential because we only need to compute n by m positions before we know the answer and can exit early. However, we do use extra space to store our memo. Okay, for our third solution, we can convert our recursion to a dynamic programming approach. As we saw earlier, the answer to each position in the grid can be solved with the information from the position above and to the left of it. So we can simply compute and store the answers from left to right, top to bottom, using the formula written here. So this is going to be the solution. Let's look at the bottom part first. As you can see, we iterate through the positions in the grid. We start in the second row and column because the first row and column require special handling, which I'll get to in a moment. If the grid is an obstacle, we set the DP value to 0 because there are no paths that can make it to this position. Else it is not an obstacle, and we simply apply the formula from earlier to compute this DP value. Finally, we return our answer, which lies in the bottom right corner of the DP table. The top part of the solution is initializing the DP values for the edge cases. The edge cases are the top left corner, the first row, and the first column. The top left corner's DP value is always going to be 1 because there is one way to be in the starting position. For the first row, it is just going to be filled with 1s until we reach an obstacle. Then all the positions at and after the obstacle are going to be 0. This is because once we encounter an obstacle, and because we can only move right or down, there is no way to reach the positions to the right of the obstacle in the first row. Similar concept for the first column. It is going to be all ones moving downward until we encounter an obstacle, and after that, all the positions below are unreachable, so they will be 0. We can simplify the initialization code a bit by doing this. You should check for yourself that it does the same thing. For time and space complexity, we have O of nm for time because of the nested ij for loop used when computing the dp table. For space, the extra space used by the dp table costs n by m, so no improvement from our previous solution, but we have the advantage of not having to use recursion. Okay, now for some follow-up questions. The first is to try and improve the space complexity of the previous solution. And the second follow-up is that earlier I mentioned we are not allowed to modify the input. However, if we are allowed to modify the input, try to come up with a solution that improves the space complexity even further from follow-up question 1. I'll post the solutions to these follow-up questions on my website, which I'll link in the description. Anyway, that's it for this video. Thank you for watching and good luck on all your interviews.